Now our next definition, we're going to extend this idea of a joint distribution to continuous random variables. And the definition here is going to look very similar to that for discrete random variables, only we're dealing with integrals rather than summations. So let x and y be two continuous random variables. The joint probability density function, or joint PDF, is a function f of x, y that satisfies these three properties. So the first property says that the function has to be non-negative for all x and y. The second says that if we integrate the joint PDF over all values of x and y, that should equal 1. And the third property tells us how we're going to use this joint PDF. In order to find probabilities that x and y take on values in some set, we're going to integrate the joint PDF over that set S. And then likewise, we define the marginal distributions in this way. The marginal PDF of x is denoted f sub x of x, and we're going to integrate the joint PDF over all values of y. And likewise, to find the joint PDF or the marginal PDF of y, we're going to integrate the joint PDF over all values of x. So let's look at this joint PDF. So x and y are two continuous random variables. X takes on values between 0 and 1, and y takes on values between 0 and 2. And the value of the joint PDF is equal to 1/2 over those values of x and y, and 0 otherwise. So first let's verify that this function satisfies the first two properties of a joint PDF. So first of all, note that this function is always greater than or equal to 0, so that's not an issue. The second, we need to integrate the joint PDF over all values of x and y. And so the joint PDF is 1/2. We're going to integrate for x goes from 0 to 1, y goes from 0 to 2, and we integrate that using basic Calc 3 techniques, and we get 1. So it satisfies the second property. Now next let's find the marginal PDFs. And so the marginal PDF of x says that the definition says we're going to integrate our joint PDF over all values of y. So integrate with respect to y. Y goes from 0 to 2, and then that's just equal to 1. Likewise, the marginal PDF of y is we're going to integrate with respect to x over all values of x, which is 0 to 1, and there's our marginal PDF. Okay. Now look at one thing this tells us is that notice that x takes on values from 0 to 1, and it has a constant PDF. That means that x is uniform over that interval. Likewise, y takes on values between 0 and 2 and has a constant PDF, and so it is uniform over that interval. So x and y all by themselves are uniformly distributed. Now, what could we do with those marginal PDFs? Well, don't let that qualifier marginal scare you. Marginal simply means that we're using this PDF in the context of another random variable. So these marginal PDFs we can use just like any other PDF that we've used earlier this chapter. We can use it to calculate values of the random variable. So for instance, if I want to find the probability that x is less than or equal to 2, by definition I'm going to integrate its PDF over all values of interest. In this case, I'm interested in x between 0 and 1/2. So integrate its marginal PDF, which is just a constant 1. Integrate that, and I get 1/2. So again, these marginal PDFs aren't any different than the PDFs we've worked with before, except that they're being used in the context of another random variable in another distribution. Now, let's illustrate how to use the third property of a joint PDF to calculate a probability. So let's, for instance, find the probability that x is less than y. And so by the third property, we're going to integrate the joint PDF over all values of x and y that satisfy this inequality. And so to help us set up this integral, it might be helpful to sketch a graph of all the possible values of x and y. So x goes from 0 to 1, y goes from 0 to 2. So this rectangle here represents all possible values of x and y. Now we're interested in those for which y is greater than x. So we're going to divide this region up into two subregions with the line y equals x. And I'm interested in the region for which y is greater than x, and so that's this region up here. So I'm going to integrate my joint PDF over this two-dimensional region. So in mathematical notation, this probability is equal to the double integral of the joint PDF, and we'll integrate dy dx. So we're going to set this up just like a Calculus 3 problem. X goes from 0 to 1, so those are my limits there. And we say for a fixed value of x, what are the smallest and largest values of y in terms of x? Well, y goes from x up to 2, and so that's the limits there. And then I integrate that, again using basic Calculus 3 techniques, and we get our probability of 3/4. In our next definition, we're going to define the idea of independent random variables. And this definition is very similar to the idea of independent events that we talked about back in Chapter 1. Events were independent if the probability of their intersection was the probability, or the product of their probabilities. Well, independent random variables, or random variables, are said to be independent if their joint PDF is the product of their marginal PDFs. Now, informally, independence means that the value of one does not affect the value of the other. Just like back in Chapter 2, independent events, the occurrence of one had no effect on the probability of the other. So let's look at a couple of examples that we've done here. In example 2, we calculated the marginal PMFs to be x cubed over 3 and y over 6. Well, if we multiply them, we get x cubed to y over 54. Well, that was exactly the formula for our joint PMF, excuse me. So that means that these two random variables, x and y, are independent. So informally, what that tells me is that if I know the value of one of the random variables, I don't know anything more about the value of the other variable. In example 3, we calculated our joint PDFs to be, or excuse me, our marginal PDFs to be 1 and 1/2. If we multiply them, we get 1/2, and that was exactly the value of our joint PDF. So again, these two random variables, x and y, are independent by definition. Now, to show that two random variables are independent, we need to first have their joint PDF and then find the marginals and show that the product of the marginals equals the joint. Well, in some practical applications, we can use the idea of independence to find the joint PDF. And that's what we're going to illustrate here in this example. Suppose a man and woman agree to meet at a restaurant sometime between 6 and 6:15 p.m. Find the probability that the man has to wait longer than 5 minutes for the woman to arrive. And so first of all, let's define our random variables. So let x and y denote the number of minutes past 6 p.m. that the man and woman arrive, respectively. So x is for the man and y is for the woman. Now, we're going to make two assumptions about these random variables. First of all, we're going to assume that both of them are uniformly distributed over the interval 0 to 15. Now, based on the given information, that seems like a reasonable assumption. They're going to meet somewhere between 6 and 6:15, and it's kind of reasonable to assume that all of those values are equally likely, more or less. So this is a reasonable assumption. Now, that tells us that the distribution of x is just 1 over 15, and likewise the distribution of y is just 1 over 15. So they have the same marginal PDF. And again, they take values between 0 and 15. Second assumption is that they are independent. So that means that their joint PDF is simply the product of their marginal PDFs. So it's 1/15 squared. So there we got a nice simple formula for their joint PDF. Now, we want to know the probability that the man has to wait longer than 5 minutes. Well, in terms of my random variable, that means that the woman arrives more than 5 minutes after the man, or y has to be greater than x plus 5. And so, by a third property of a joint PDF, to calculate this probability, we're going to integrate the joint PDF over all values of x and y of interest. And so to set up this double integral, we could sketch a graph similar to what we did in the previous example. X goes from 0 to 10 in this case, because if the man arrives after time 10, he's not going to have to wait longer than 5 minutes. Again, assuming that the woman really does arrive by 6:15. So that's why this goes from 0 to 10. And then for a fixed value of x, y goes from x plus 5 up to 15. And then we integrate that using standard calculus 3 techniques, and we get our probability of 2/9.